Okay, so we've got question lesson 6.1c on Hooke's law. Now, Hooke's law really can be described by this formula. F is equal to negative kx. And it's probably the best way to describe what is Hooke's law is by first of all running through the formula. The first thing is that F is the restoring force of a spring. Okay. K is the spring constant, and X is the displacement. Okay, so if we've got, let's say, a spring and we're stretching it, and we stretch it some distance k, or x, sorry. We've pulled it this direction. The spring is going to act in this direction, forcing it back with some sort of spring constant k describing how stiff the spring is. So this is the spring stiffness, if you will. How much force is going to get. Now, the negative is there because the force is in the opposite direction. Of the x. Right? Just as we described up here at the top. Right? Force was going this way, the restoring force, where x was going the other way. We've moved the spring this way. The spring is going to pull us back this way. So, if we think about if something is vibrating back and forth in simple harmonic motion, let's say that I've taken the spring and this object is bouncing up and down. Where would we see the maximum acceleration? Well, maximum acceleration implies maximum force. Will be where we see maximum acceleration. Maximum acceleration force is going to be where we see the most displacement, right? And that is at the amplitude. So we're going to see the most acceleration at the amplitude because we have the most displacement there, which means the most force. So where would we see the maximum speed? Again, if we've got this spring and it is moving up and down, well, if we've got amplitudes here and here, that's where we're going to see the most acceleration. As we move through the equilibrium is where we're going to see the maximum speed. And the reason for this is because if we've got the most acceleration here forcing us this way, as soon as we go past that equilibrium, the force is going to go in the opposite way, slowing us down until we reach a stop and then push us back. And so as we go back and forth, we're going to see the equilibrium at the point where we've had the most time with the force going in the direction of motion before we have a force acting in the opposite direction. So we have most time with force in direction of motion before we get it, before a force opposing motion is in place. Right? And that's why we'll see the maximum speed at the equilibrium. Let's take a look at a couple of examples here. The first example here, we've got a restoring force upon a 0.5 kilogram object. The spring is 2 newtons, spring constant 15 newtons per meter. Now, one of the things with these spring constants is they'll always be given. Right? Or you'll be looking for it. Or it's going to be irrelevant. Such as, we're not giving a spring constant for the acceleration of a ball on Venus because there's no spring. It's irrelevant, not part of the equation, right? It doesn't matter if the object is a spring. How far it accelerates to the surface of Venus when dropped has no bearing on it, so it's irrelevant. But, so F is equal to negative kx. That force being 2 newtons equals negative 15x. And so we got 2 over 15 is equal to x, or 0.13 meters is equal to x as the displacement in the opposite direction of this force. Second question, we've got a 0.5 kilogram. It's stretching a vertical spring, 3.25 centimeters. What is the spring constant? Well, this is vertical, so it's stretching it. So the force here is going to be equal to that of gravity. So we've got a 5.0 kilograms multiplied by the acceleration due to gravity, 9.81 meters per second squared. Gets us a force of 49.05 newtons. Now you might be asking yourself, well, why with question 1 did we not just use the same thing, right? We had a 0.5 kilogram. Well, here, first of all, we're not told vertical. So you can't assume. And the fact is that the force was already given here. So we can't assume it's vertical. We're not told it's vertical. If it was vertical, the force would be approximately 4.9 newtons, and it was something different. So we're now looking for that spring constant. Right, we're going to take that force of 49.05 newtons down a displacement of 0.0325 meters, and so we wind up with a 15 or 1.5 times 10 to the 3 newtons per meter as your spring constant. Okay. Just a couple of quick notes. When we talk about elastic potential energy, we're talking about energy stored in the position based on the spring because of the spring being deformed. We've got a formula on our formula sheet that is equal to negative kx squared. Now, this is energy stored within the system due to spring deformation. Okay, and we've already got the formula there. Again, we don't worry about the negative because energy is a scalar quantity. There is no direction on it, so that doesn't matter. But the question about why is that 1/2 there? Well, if we think about a spring being like this, the spring is actually going to provide lots of forces in many directions, and the total result of the nature of that spring, so this balances the nature of a spring. Dealing with the amount of energy that's actually stored. Honestly, there's probably a big, long derivation for why that 1/2 is there, but I'm going to just leave it at that for this case. One more example here. So if we've got a spring constant and it's stretched from 15 to 20 centimeters, right? How much more potential energy? More potential energy. So we're going to find out the potential energy at 15 and at 20. In order to find the difference. Now, when you calculate this here, this is 1.1 joules. When you calculate it at 0.2, you wind up with 2.5 joules. Oh, wait, sorry, that's 1.4 joules. I should check my math. 0.15 squared times 125 times divided by 2, 1.4. And so what we see is 1.1 joules more energy. Okay, that's how many more joules of energy, which is what the question was actually asking. It wasn't asking specifically for the 15, wasn't asking for the 20, it was just asking for how much more. Okay, thanks for watching, guys. If you got any questions, let me know.